Alright, Assalamualaikum and hi to all. Okay, today we will proceed with our chapter 2, which is electrostatic fields. Right, so the objective for this chapter is for you to know, for you to know the source of field and also able to apply some law to determine the field given. So these are the two objectives that from the chapter 2. All right. So first of all, let's look what is electrostatic field. Okay, what is electrostatic field? So electrostatic can be, the words electrostatic can be divided into two. Okay, it is contains of electric and also contain of static. All right, so let's look what is electric. So electric, obviously it is a form of the field that contain of electric field at specific position. Okay, it contains of electric field at specific position. Okay, for example, E, okay, which has a vector here, okay, in a position of x, y, and z. So x, y, and z, I think you already know that x, y, and z is referring to the Cartesian, and if E vector is referring to R, P, and Z, so it is a cylindrical, and if E is referring to R, theta, and phi, so it is referring to spherical, right? I think we have covered this in previous chapters. So these are the electric field. Okay, so in this case, we are neglecting, or we are only considering electric field, and so that means is we are neglecting, or we are or we are not taking into account the magnetic field. Okay, we are neglect the magnetic field. All right, so we are only considering the electric field. So this is referring to electric field, okay, where it is related with the position, okay, the position of where the electric field is, yeah, either in a Cartesian, cylindrical, or spherical. Okay, so now let's move. What is static? Okay, so what is static? So static means it's referring to usually electric field is in respect to time. Okay, electric field respect to time. So let's draw axis here, where this is the electric field. Okay, electric field where the magnitude here, and this is the time. So this graph is showing the electric field in respect to time. Okay, electric field in respect to time. Okay, so let's say that we have one particular condition where the electric field, okay, appear to remain constant throughout, okay, throughout any time. Okay, so there are going to be no changes of time. Okay, there are going to be no changes of time, and the time now is constant. All right, so it will be there, since that there will be no changes of time, so d over dt can be cancelled. All right, so the field now, we can say that the electric field now is independent of time. Okay, so the electric field now is independent of time. Okay, right? And therefore, in this case, in this case, we can ignore. We can say that we are ignoring. In this case, we are ignoring. Okay, we are ignoring the time. Okay, any term respect to time. So we are ignore any term that respect to time. Okay, any term respect to time. So we are simplifying actually in for electrostatic field. Okay, there are two conditions where we are simplifying. Okay, we are simplifying the definitions of electrostatic. Okay, first one is our interest is only on electric field. Okay, our interest is only on electric field. Okay, we are neglecting the magnetic field. And the second things, okay, that we are simplifying is we ignore any term respect to time. Okay, so we are simplifying the electrostatic field. Okay, so we are simplifying the learning process. Okay, where our field of interest, is only component component only component of field, which is electric field. Okay, and our interest is the field. Okay, field of our interest. The field of interest is independent. It is independent of time. Okay, it is independent of time. So instead of usually we are writing the electric field. Usually, we are writing the electric field X, Y, Z, and T. Okay, since that we are independent of time, we are neglecting the time, so we can cancel the time. So we can just write electric field is X, Y, and Z. All right, so I hope you are clear. Okay, in this chapter, we are simplifying the learning process. Okay, by only considering the electric field, and only we neglect the any terms respect to time. And however, at the end of the course, okay, at the end of this EMT course, we will still use the same concept. Okay, at the end of the EMT course, we will still use the same concept where the electromagnetic field is independent of time. Okay, this independent of time we're going to use throughout the course. Yeah. However, during at the end of the course, the difference will be there will be two fields appear. Okay, there will be two fields appear, which is electric field and magnetic field. Okay, so since that this is at the beginning, so at the beginning we only considering the field component. Okay, and we will learn electric field, the combination of electric field and magnetic field at the end of the course. And but we are still considering that the term is independent of time. All right, we always say that it is independent of time, where we are neglecting the time. Right, so these are the learning process. So let's proceed with the chapter 2. Okay, how the electric field can be generated. Okay, how now we are questioning ourselves how the electric field can be generated. Okay, so then we need to know, okay, in order to know how the electric field can be generated, first of all we need to know the sources of electric field. Okay, so the sources of electric field, so there are 4 types of sources. And before we go into detail, okay, the 4 types of sources, let's look at the common behavior of electric field. Okay, what are the common behavior of electric field? We said that the common behavior of electric field is always stationary charge. Okay, the behavior of electric field is a stationary charge. So it means that what it means that the charge is not moving at all. It is static. Okay, it is not moving. If the charge is moving, okay, if the charge is moving, it is known as current. Okay, if the charge is moving, okay, so we know it as current. Okay, so common behavior of charge. Okay, when we say charge, so it is a static. Yeah, it is not moving. So once it is moving, it is known as current. All right. So current is not the source of electrostatic field. Okay, current is not a source of electrostatic field. Only charge will be the source of electric field. Okay, or electrostatic field. All right. So in order to see the charge, we need to develop model. Okay, in order to see this charge, we need to develop model and relate that model with specific language called mathematical equations that we have. I think that's why we have learned earlier in chapter 1, the preliminaries mathematical. Okay, because we need to relate the model, okay, with specific language that called as mathematical equations. So let's look what are the 4 types, categories of sources. So we have point charge, okay, we have line charge, we have surface charge, and we have volume charge. So these are the 4 categories of sources. So let's go through in detail each of the categories. Yeah. So let's look what is the point charge first. Okay, what is a point charge? So for point charge, it is a very simple. Okay, this is, I think it's very simple. So let's assume that we have a point here. Let's assume that we have a point here. Okay, so this point have a magnitude. Okay, have a magnitude of charge, and the magnitude is represent or symbol as Q. Okay, so this point charge is represent or symbolized as Q. Okay, so Q here can be the unit. Yeah, the unit for this Q here is called coulomb. L-O-U-M-B. Yeah, coulomb. All right, it is C-O-U-L-O-M-B. Sorry, C-O-U-L-O-M-B. L-O-M-B. Okay, coulomb. Okay, it is no the unit for this Q. Okay, Q is referring to the charge symbol or the magnitude of charge, and the unit of it is called coulomb. All right, and it can be, instead of write the coulomb here, so it can be simplified as C. Okay, it can be simplified as C. All right. So this is point charge. Okay, so it is very simple. This is a point charge. Okay, and then let's look into line charge. What is a line charge? Okay, so line charge is actually a combination of several point charge. Okay, combination of several point charge that will form a line. Okay, for example, we have a line. Let's say that we have a line here. Okay, this is a line, and this line is actually made of a combination, or it contains of many of point charge here. Okay, so combination of point charge will make a line. So let's say the point, yeah, there's going to be point here, point here, point here, point here. So lots of combination of point charge, it will make a line. Right, so that's why we have to know what is point charge first before we know what is line charge. All right. So it can be represented in any shapes. Okay, there is no specific shape for line charge. It can be any shapes. All right. So let's say, okay, so a line charge here. So line charge here is equal, okay, to total charge Q. Okay, as I mentioned earlier, that line charge is actually a combination of several point charge. So the total charge in line charge is a total charge Q. Okay, these are the first information that we can get from the line charge, where the total charge is Q, which is the amount of each point charge, amount of each Q of point charge. Okay, so the each amount of point charge, Q of point charge carry will okay, the total of each of the point charge will going to be the total charge for this line charge. All right. So this is the one information. The total charge is equal to Q. Okay, where the Q is actually the sum of uh, point charge. Okay, the sum of point charge value, and then another information that we can get from this line charge is the total length. The total length, okay, form is known as L. Yeah, this is the total length. Okay, so these are the two important information that can be observed from the line charge. Okay. All right, so let's assume that the line charge is very big in structure. Okay, let's assume that this line charge, it is a very big in structure, and in this case, yeah, in this EMT course, we need to take a sample. So in order to evaluate this line charge, since that it is a big in structure, so in order to evaluate, we will take a sample of the structure. Okay, so let's take a sample of the structure. For example, I take a sample of this line charge structure at this point. Okay, at this point. All right. So it will be the sample of this at this point. Yeah, it will be dq perpendicular to dl. Okay, where what does that mean? It means that a small amount of Q, a small amount of charge, is proportional with the length of the line charge. Okay, the small amount of charge is proportional with the length of the line charge. Right. So the longer the line, okay, the longer the length. Sorry, the longer the length, not the longer the line. The longer the length of this line charge, there will be more charge, more Q charge of the sample carry. Do you agree with me? The longer the length of this line charge, so the more Q charge the sample will carry, right? Okay. So now, okay. So now, let's look the mathematic in this mathematical form. Yeah. So dq, okay, dq. This is q. Sorry, this is q. It looks like theta, but it is q. Okay. Sorry for my handwriting. This is q actually. Okay, so dq proportional to dl. How to make it as a mathematical form? We can rewrite it as the equality. Okay, instead of proportional, we want to change this form to equality form. So in order to change this proportional form to proportionality form to equality form, we need to have a constant there. So dq equals to rho L, which referring to this length, yeah, rho L times with dl. Okay, so this rho L, is referring to the line charge density. Okay, it's referring to line charge density, where the unit is coulomb per meter. Okay, coulomb referring to the total charge, okay, or q, the total q, and meter referring to the total length, all right. So this is how we can rewrite this proportionality form into equality form. All right, so we have to introduce one's constant here, which is rho L. Okay, so let's say that there is a question. Okay, let's say there is a question, and the question asks about the total charge carried by the line charge. For example, we have a line charge here. So the question asks, what is the total charge carried by this line charge? So we can calculate Q, which is the total charge, integration. Okay, we are now using the integral. Okay, the integrals, since that this is because that the line that we are dealing with is a continuous form, yeah, and the charge at each point. Okay, let's say, for example, you are taking this point, yeah, this point of charge. If you are taking this at this point of charge, it is same. Okay, the q, it is same as dq proportional to dl. So anywhere you can choose anywhere the point where is the point charge is, yeah, so it's same. So that's why you are allowed to use we can use integral because it is a continuous, yeah. And in order to get the total charge of the line, of this specific line, so q is equals to integral dq, okay, dq, all right, where q here is the sum of point q, all right. And we can rewrite this as, since that dq is equals to rho l dl, so we can rewrite this as integral rho l dl. Okay, so this is how we want to find the total charge for this line, yeah. So integral rho l dl. Okay, so I hope it's clear. Okay, so let's proceed to the surface charge. Okay, let's proceed to the surface charge. So for surface charge, let's consider or assume that we have a surface. For example, that we have a surface here. We have a specific surface here. Okay, and this is the surface. And from this surface, there are two important information that we have. First is the total area of this surface. Total area. Next is the total charge, which will be QC, right? Total charge. So these are the two important informations that we need to find from this, or we can get from this surface charge. So same as before, okay? Same as before, in order to find, okay, the total charge, or in order to deal with this kind of charge, what we need to do is we need to take a specific sample, small sample, to calculate the surface. So now let's assume that we are dealing, or we are taking this small sample, and this small sample have the total, the amount of charge is dq. Okay, very small amount of charge, which is dq. Okay, so in this case, we can write the equation where dq is proportional to ds, where s is referring to the sample size. Okay, the size of sample. Okay, so our total q now is depending on the size of the sample. Okay, our total q now is depending on the size of the sample. The larger the size of the sample, okay, size of sample, sorry, size of sample, the larger the size of sample, the more amount of total q we will get, right? So now this is in a proportionality form. So how to change this proportionality form to equality form? So same as before, we need to introduce one constant, yeah? So dq is equals to rho, still rho, and then now it is s, yeah? Rho s, it means that rho to the rho is referring to the surface, yeah? And ds, okay? So rho s here is referring to the surface charge, yeah? Surface charge density. Okay, surface charge density, where it is going to be coulomb per meter squared. Okay, why meter squared? Because we are dealing with a surface, right? So it is going to be column over meter squared. So let's say that we want to find or we want to calculate the total charge of the structure, of this structure. So we can calculate. We still can use, we still need to use integral, okay? But now our integral, we're gonna be double, okay? Double integration because we are dealing with surface, yeah, surface, double integration. So it will be rho s ts, okay? So the mathematical now becomes more complex, okay, due to deal with surface, okay, because we are dealing with surface, okay, so it will be a bit mathematical complex, yeah, right? Because we have double dimension, we have to take into account the width and the length of the surface, yeah, because we have double dimension. So this is how we want to find the surface charge. All right, so now let's proceed to the next category, categories where volume charge, okay, volume charge. So volume, in terms of volume, let's say that we have let's say that we have an area here, okay. So what are the information that we can get from here? We can get the volume dimension, okay, the volume of this design of shape, okay, the volume of it. And then we can also, another important information that we can get is the total of charge, okay, which is q column, q and the unit is column. All right, so same as surface charge just now, in order to calculate the total charge, yeah, in order to calculate the total charge, what we need to do is we need to take a sample, okay, we need to take a sample, here, and this sample have dq, okay, the amount of charge it carry is dq, and we can write the equation, okay, where dq is proportional with the volume dimension of this particular shape, yeah. So how to change this integral in proportionality form to equality form? So same as before, so it will be dq, okay, equals to rho v, where now the v is a volume charge density, and then times with dv, okay. So now the volume here, the rho v here referring to the volume charge density, okay, where the unit will be coulomb per meter cubic, all right, and dv is the dependent, is dependent to the coordinate system, yeah, dependent to the coordinate system. Okay, what does that mean? It means that if this system is a it is a cylindrical, so our dv that we're going to dealing with same as what you have learned during what we have learned in chapter 1. So it will be for example, yeah, if it is a cylindrical, okay, I hope you still remember, if it is cylindrical, so dv will be, so dv will be, okay, dv will be r dr dv dz. Okay, so that's why it is very important for you to understand the coordinate system in previous chapter. So this is if dv is if the shape is in a cylindrical, but if the shape is spherical, so the dv will be equals to r squared sine theta d theta d phi and dr, right? So that's why you have to understand the previous chapter very well, okay. So dv is depending on to the coordinate system, which coordinate system that we are dealing with, yeah, all right. So for example, For example, we want to find the total charge of this system, of this particular shape, all right? So in order to find the total charge, so Q will be, now the integral will be much more complex. There will be triple integration, okay? And then what, integral V dq, and then dq is integral V, it will be rho V and dV. Okay, so it will be triple integration. And how to solve it based from the structure, okay, the shape of the structure. If it is a box, so we can use dv is equals to dx dy and dz. If it is a cylindrical, we can use this dv, okay, dv is equals to r dv dv dz. If the structure is a spherical, so we will use dv is equals to r squared sine theta dr d theta, dr d theta and dv, right? So I hope up until here you clear with the concept of this electrostatic field. So these are the concepts. So let's look example. Let's look one of the problems. So for example, that we have a problem here. Okay, you need to determine. Okay, determine the total charge contained in line charge distribution where rho is x, y, and z, okay, is equals to 2x plus 3y minus 5z, okay, where the unit is coulomb per meter, okay, extending from 3 to 1, these are the coordinates, to 5, 4, 7. Okay, so the question now say, okay, determine the total charge. So what you need to find the total charge. Okay, you need to find the total charge contained in a line charge. Okay, so contained with a line charge, since that it is a line, so it's comply with the unit here, okay, which is coulomb per meter, so it's referring to the line charge. Okay, so distribution is rho x y z. Okay, so it's using a Cartesian. Okay, 2x plus 3y minus 5z. So this is the this is the equation, yeah, the position vector. So this is the equation. Okay, extending from, this is one of the coordinate, 3 to 1 to 5 4 7. Okay, so let's draw the the diagram first. So let's say that you have a line here, okay, and one point is 3 to 1, and the other point is 5 4 7, and you need to find, the question asks you to find the total charge contained in this line, okay, where the equation is rho L is equals to 2x plus 3y minus 5z. So these are the equation for this line charge distribution. And what you as I mentioned earlier, in order to deal or to solve this kind of equations, yeah, you can take one point. Okay, you can take any point. You need to choose any point. Yeah. So here, okay, so here, yeah, in this line, yeah, in this line charge, this line is not specific as a straight line. Okay, we are engineer, so we can assume that the line can be crooked. The line can be in a it moves like this. Okay, the line can be like this, the line can be like this, so it can be any line. Okay, so first of all, that's why it is very important for you to draw the diagram, because you want to imagine how the line distribution look like. Okay, so in my case, I'm considering that the line is simple by taking a straight line. Okay, so actually it's up to you. Yeah, you can assume the pattern of the line can be anything. Okay, so your solution will be depending on how the pattern of the line will be. Okay, so in my case, I'm taking the the simple straight line. So my solution will be simple straight line. Okay, so in order to find the total charge, okay, now I need to find the total charge. So the total charge will be, okay, the total charge, okay, this Q, this will be equal, okay, based from this point line charge. So the total charge is integral rho L dl. So total charge Q is equals to integral rho L dl. Okay, now dl is the magnitude. Okay, so we are dealing with the Cartesian now. Okay, Cartesian, so dl is equal with the one that we have learned in chapter 1. dl in Cartesian is dx plus dx at x direction plus dy along y direction plus dz along z direction, right? And in order to find the magnitude, since that this is in a form vector, right? But in this case, the total charge is in the magnitude. We need to convert this from form vector to magnitude form. So it will be square root of dx squared plus dy squared plus dz squared. Okay, I hope up until here it is clear, right? So now, so now it will be, in order to find the total charge, so the Q will be integral of rho L is this equation, right? So it will be 2x plus 3y minus 5z, okay? And dl now will be this one. Our dl will be this one in the magnitude form, which is square root dx squared plus dy squared plus dz squared. Okay, from here, okay, there are lots of unknown here. Okay, first of all, okay, our integral now is we are dealing with one variable. However, we have three variable in these equations, right? We have x, y, and z variable. So in that case, you need to choose only one variable. You need to decide which variables you want to deal with, either x, either y, or either z. Okay, so it's up to you. You can choose any variables that you like. Okay. So if you are choosing x variable, what you need to do is you need to convert the other variable into the variable that you have choose. Okay, for example, if you choose x, you need to convert y and z into x. Okay, so how? Let's do it together. So now let's say that I want to have, let's take x variable. Okay, so the starting point will be x equals to 3. Okay, this starting point is based from this coordinate, yeah, so it start from x equals to 3 and end at x equals to 5. Okay, and end at x equals to 5. Okay, and we have the equation of rho L just now is 2x plus 3y minus 5z, and then square root of dx squared plus dy squared plus dz squared. All right, so what we need to do next is we need to convert the other variables into the variables that we have decided earlier. So convert, our next step is convert y into x. All right, so how to convert that? Okay, so we need to use the x minus 3. Okay, x minus 3 is the origin, okay, over the origin of y coordinates is the origin of y coordinates is 2. Okay, so it will be y minus 2. Okay, so x, what is the destination? Okay, what is the destination? So the destination is 5 minus 3. So it will be 5 minus 3 over, at the y-axis, 4 minus 2. Okay, so over 4 minus 2. So we will get 5 minus 3 over 4 minus 2 is equals to 1, right? 2, 2. So we can rewrite this equation, x minus 3 over y minus 2 equals to 1. So from here, we can write that y is equals to x minus 3 plus 2, where y is equals to x minus 1. Okay, so now we already convert y into x. The next step is we need to convert another variables, yeah, the z variables. So convert z into x. So we can use the same method. So z is minus 1 because the origin is 1, all right? And then over x minus 3, where the origin is 3. And then 7 minus 1, which is 7 here, minus y, 1 here, which is at the z-axis. Okay, 7 minus 1 over 5 minus 3. Okay, this numerator and denominator, it can be the other way around. It's also okay. Okay, it is not specific x over y, z over x. It can also be y over x or x over z. The other way around, also you will get the same, the same equations, yeah? So in this case, we will get the final answer. We're going to get z is equals to 3x minus 8. Okay, so now we already have the y in terms of x. Okay, we already have y in terms of x and z in terms of x as well. Okay, and we can include this. We can include this into here and include this into here. Right, so now left behind, how about the dx, dy, and dz? Okay, so y, how about the dx, dy, and dz? Right, so we need to solve this part. Okay, so here, okay, here, let's say we want to solve this part. Now we are dealing with this part. Okay, now we are dealing with this part. Okay, so we can rewrite the equation. It will be dx over dy over dx squared plus dz over dx squared. Are you agree with me? We can rewrite this into this. Okay, where we factorize the dx. Okay, all right. So from here, since that we have just now the dy, the y equation and the z equation, we can find the differential of dy over dx squared, right? So dy over dx can be rewrite as y x minus 1, where we have find earlier, right? And dy over dx will be 1, all right? And for dx, so dz over dx is from where we got earlier, where z is equals to 3x minus 8. So we will get dz over dx is equals to 3. Okay, so sorry, this is not final yet. I can't use this sign actually because this sign is referring, it is final. Okay, all right, so we can include this inside here and include this inside here. So we can rewrite in order to solve this equation, in order to find the total Q, we can solution, yeah? Solution to find the total Q for the question. Q is equals to integral x from 3 to 5, and then it will be 2x plus 2x plus, sorry, 3x minus 1 plus, sorry, not plus, minus, right? Minus 5, 3x minus 8, and then dx square root of 1 plus 1 squared plus 3 squared. Okay, so I leave it to you for you to find the final answer. All right. So I hope up until here is clear, and later on I will paste another few questions. Okay, so let's try that question as well so that we can discuss during our online class. All right, so if you have any questions, okay, if you have any questions related to this chapter, please let me know. You can write down in the Padlet link that I will provide later. All right. Thank you.